thank you for coming. We have a really big room for a small crowd, but it's better than the opposite if you wanted to listen and there's no room to sit. That's a bad situation. So my name is Harun Bayraktar. I'm the engineering manager for Cuda math libraries at NVIDIA. And Tim Costa, whose name you see up there, he's our product manager for math libraries. And I'll be showing the work of all my great engineers. I actually haven't written a line of code of any of the results that you'll see up there, so I'd like to give them a shout out. All right, so a quick overview, and I want to introduce this machine in case you've missed it, or an appliance as Jensen sometimes calls it, because there's a bunch of results on that system for math libraries. But we'll talk about the kind of things that we're focusing on, initiatives. We'll talk about some of the libraries and some of the new things that we're doing, and then towards the end I'll show some results for multi-GPU performance. It's one of the most commonly asked questions and hot topics these days. All right, so what are the Cuda math libraries? So I don't manage all the libraries at NVIDIA. There's many of them, and you'll see deep learning libraries like cuDNN and Tensor RT are not on this list. But CUBLAS is, and that's very heavily used in deep learning as well as in HPC, obviously. So the linear algebra libraries are on the top, and then we're also responsible for the RNG, signal processing, math API, and CUTLASS is not directly in my team, but we work very closely. And in case anybody here is interested, our team's also responsible for the image processing libraries, but that's kind of out of the scope of this discussion. So what are the things that keep us up at night, or the things that we worry about at NVIDIA? One of the big things for us, obviously, is performance. That's our major focus. And we keep revisiting algorithms. We tune them. If you're in a corner case, for us, you might find yourself maybe not experiencing this, and at my last slide we'll tell you to please give us feedback if that's the case, but we focus on certain, as many applications as we can and keep tuning performance. We add whole new libraries, so I'll give you a link or a plug for another talk about CUTENSOR. It's a brand new library. We also did a device extension library that I'll talk about. We are heavily focused on multi-GPU, which is why I wanted to introduce the DGX2. It's a 16 GPU, 16 volta GPU system with a proprietary NVLink and NVSwitch interconnect. And then a single GPU focus. One of the things that's quite interesting and was mostly motivated by deep learning is mixed precision and reduced precision computing. And that introduced the Tensor cores inside NVIDIA GPUs, and later followed by Google and their TPUs with the bfloat format. Our GPUs use the FP16 format. But there's a big question about, can we use them for something other than doing gems and fully connected layers in deep neural networks? And we try to answer that question with a yes, and hope that you can answer and solve many other problems with it too. So with cuSparse, we actually went back to the drawing board, and for some of the most commonly used kernels, which are the SPVV, SPMV, and SPMM, we implemented a new generic API so that you don't have a different API for each type or all the different options that we might have. So what we did is we're deprecating some of the old APIs, and these were introduced with Cuda 10.1, and then we extended platform support for them, and the performance is dramatically improved compared to previous implementations. The chart you see on the right-hand side is compared to a Xeon Gold, two-socket Xeon Gold, using all the cores and comparing some of the sweet sparse matrices in a sparse matrix vector multiply scheme. CUBLAS, probably along with cuFFT, the most heavily used library in all areas possible. We had a number of improvements starting with Cuda 10.1. The first one was we introduced a new mini library, let's say. It's only focused on matrix multiplication. And before you have a reaction, oh no, yet another library, which happens a lot. CUBLAS LT was necessary. It gives you advanced matrix multiplication functionality that does not fit into the legacy CUBLAS APIs. So we decided to create a new API that allows the users to get as much degree of freedom as CUBLAS can offer, and some advanced features that some of them are more applicable to deep learning, such as integer matrix accumulate. So Turing GPUs, for example, introduced IMMA, Tensor cores, and you can get some unbelievable numbers like 200 teraops on a single card. So if you want to access it at that level, you have to use this API because it requires special layouts and some special options. So we created this. And it also lets you do auto-tuning type stuff. So if you want to squeeze, if you want to find out on your particular system a few more percentage of performance, you can use these APIs to do that. We've been removing the restrictions on tensor cores, and hopefully we'll continue to do so in future releases. And then we keep improving performance. It's a major challenge to offer peak performance for all gems, but we keep trying and continuously improve it release to release. In Cuda 10.2, we increased the workspace size, so for large gems, this made a pretty big impact. And then we have an early access release that I'll talk about in a second that allows you to run multi-GPU with better performance than the legacy CUBLAS XT library. So I mentioned this a moment ago, tensor cores. What do? So let's talk about them on the left-hand side of this chart. So the chart on the left has three different precisions, FP64 on the far left, FP32 in the middle, and FP16 on the far right. And the left y-axis is the number of bits in the floating point representation assigned to the sign exponent in mantissa. And then the right-hand side axis, this is one of those fancy double vertical axis charts. That's the green line, is how many teraflops you can get on a Volta GV100. So with FP64, you get about 7.5 if it's a Tesla card. With FP32, you'll get twice that, close to 15. And if you go to FP16, thanks to the tensor cores, you get, boom, all the way up to 125. And one thing that gets confused a lot, tensor cores only take the input at FP16, but the multiplication happens with no loss of precision, and the accumulation happens at FP32. So as long as you can scale or reduce your data and not lose information during that on the input to the matrix multiplication, you don't lose any information beyond that. And it has been, I've gotten a lot of comments that make me clarify it every time I get a forum. Of course, if you multiply a bunch of FP16 numbers and do FP16 arithmetic, you're going to get a lot of loss. But that's not what happens inside the tensor cores. You don't lose so much precision. So it's only at the input phase. And if you look at our documentation, there's quite a bit of detailed explanation. Oh, sorry. So now the right-hand side of the chart. So common solvers are matrix multiply dominated, LU, Cholesky, QR. And tensor cores are great at multiplying matrices. So can we use it? How can we accelerate it? And the answer is yes, otherwise we wouldn't be asking. And the idea is very simple. Take blocked LU factorization, which is shown on the right-hand side. The idea is you take the block LU factorization, you can do your panel we do it at FP32, but you can do it at any precision you want. You don't want to lose a lot of information here. And the only part where you would apply the tensor cores is the Schur complement update for the trailing matrix. And that's actually where bulk of the flops are in a LU factorization. So if you do that, you get a very fast factor, right? How fast? Quite fast, it turns out. So in Cuda 10.2, we released something that already existed in Magma, but our implementation is different than Magma's. Magma in end of 2018 released the real version, and it uses the hybrid CPU and GPU. With Cuda 10.2, we released both real and complex LU solver in CUSolver in the Cuda toolkit. And I'm showing some performance numbers on the left-hand side here. The x-axis is the growing matrix size all the way up to 30,000. Results are in a single GV100. It's a Volta GPU. And the y-axis is teraflops. And the red line is what you would get if you just used our LAPACK implementation on the Volta, which gets, for large matrices, up to 6 teraflops. If you do iterative refinement and use the LU factor that we got as a preconditioner to it, or the residual correction solver to it, which is basically the key idea here, you can get a 2x speed up there and still get a FP64 quality solution because you're controlling the conversions on the residual. And then the green line is if you go all the way down to FP16. So in reality, 3 levels of precision are happening here, and all of these results are the same, which we can verify. And for a double complex, you can get up to a 5x speed up for a 30K matrix. So some details about the solver availability and support is on the right-hand side. We support single and multiple right-hand side solutions, although the single right-hand side solution runs fastest with GMRes as the iterative solver that uses the preconditioner. And the multiple right-hand side in this version is a classical iterative refinement. And if you want to know the details of this, I highly encourage you to go to Azam's talk. He's the lead author of a supercomputing paper from 2018. He's in our team, and he's going to be talking in detail about this tomorrow, just before lunch. So make sure you don't miss it. All right. How many people here have heard of CUTLASS? Great, there's more than one. That's very good, I'm very happy about it. So if you want to get CUBLAS-like performance, I would say there's no better tool than using CUTLASS, and you have to do something different than what CUBLAS just offers outside the box. CUTLASS is an open source template library for those that are not familiar with it, and can let you go all the way from thread-wide, warp-wide, block-wide, or CTA-wide, whichever terminology you're used to, and device-wide primitives. So you can build, or use the building blocks that CUTLASS offers to build your own library. It's used by many people that want to write fused device kernels, let's say, into their kernels. And this is something that would allow you to do that. One of the things that was heavily requested by users was the way Cuda exposed tensor cores originally was only through the WMMA instruction, through the Cuda API. And if you have actually done that, I'm not going to do a show of hands because it's very, very few people in the world and the odds are really small. If you've done that, you would have noticed that you don't quite get the performance that you would expect. So what NVIDIA did with Cuda 10.1 and also CUTLASS 1.3 is kind of showing you how to use it, is the PTX instruction that allows you to directly access the hardware functionality is exposed for Volta. In Cuda 10.2, it's exposed for Turing. And the chart on the right-hand side, which I don't have to go into the detail, shows you the performance of a CUTLASS implementation relative to CUBLAS. And you can see that it's hovering entirely above 85% and close to 100%. And the tensor core variants are on the right-hand side. I should have put a version of this chart a couple, like 18 months ago. The right-hand side bars were quite a bit lower than CUBLAS, and the WMMA versus the MMA sync PTX is the main reason. So if you've looked at this before and you didn't use it because of that, please visit it now. It's been opened up to give you the full access to the full performance. All right, so that's a good segue into the next topic. Am I doing it on time? All right, we should be right. So, device extensions. If you can't tell already, I like pictures a lot. So we have a Volta GV100 here, and the chip is actually here, if you haven't seen it before. Full disclosure, when I first saw it, I thought these were the HBM memories and their voltage regulators. The HBM memory is on here. And why are we talking about device extension libraries? So one thing that's happening is the chips are getting bigger and bigger. They have more shared memory. There's more register space. And that allows the kernels to grow. And now you want to do some gems and FFT, and maybe in the future even some linear algebra, go back to another FFT. You do forward FFT and inverse FFT and some other operations in between. Why should you have to pay the penalty to keep going back and forth to the global memory on the GPU, which is about 900 gigabytes a second bandwidth? It sounds very high, but it's a lot slower than accessing register or shared memory, right? And so we thought, how can we offer our implementation? So in this case, it's cuFFT, which is in industry-leading performance, and FFTs running at near memory bandwidth of the system. We found a way to offer our kernels in a form that you can inline into your kernels. So there's no round trips to memory. You can fuse it with your operations, and you can get very dramatic performance improvements. And can't say a lot, but I can say we expect this trend to continue with other libraries because, like I said, it's just a natural extension of what's going on these days. So quick example on the kind of performance you can get. We try to do as much as an apples-to-apples performance comparison as possible. The right-hand side, the y-axis is gigaflops. Apologies, there's some charts. They should have all dropped the 3 zeros. We usually talk in teraflops, but with GPUs, but there's many gigaflop numbers. The x-axis is the FFT size, and then you can see the performance comparison goes all the way up to 7, 8x easily. One question we get is, how do I use it? And we actually have a quite clever way of using something that looks like expression templates in C++, where you can define the FFT, and in the future, hopefully, other functions by using traits. So you keep adding attributes. I want to do an FFT of size 128. It's of type complex to complex. I want to go forward. I want to use 8 elements per thread. I want this precision, and I want this hardware architecture. And at compile time, our kernel will be grabbed from a blob, a binary blob, and inlined into your kernel. And you will get the kind of performance you're seeing here. This library, along with CUBLAS MG, and some of the other things you'll see, are in early access mode. And that means you can go to this website, developer.nvidia.com, Cuda Math Library EA, and sign up and ask for access. And our product manager, Tim, will approve your, you'll have to say what you're going to do with it in a few words. Give us your email. And the reason we have them in early access mode is these are very early stages and new ideas, and we want to work with users closely and kind of bake the APIs and make sure we're addressing all the use cases before we say it's a version 1.0 release, and then we have to do another quick 2.0 because we have to break all the APIs because we missed something. So you'll see a number of early access releases coming. All right, I have a couple minutes. CUTENSOR is a tensor contraction and element-wise operation library that significantly outperforms a CPU implementation. This y-axis again is gigaflops, x is different cases with growing arithmetic intensity, hence the flops are going up. If you're interested in tensor contractions or element-wise operations, INSUM summations, things like that, this library is fully available, and Paul Springer, who's the lead engineer who actually implemented this library, is going to be talking about it at 4 p.m. today in room 607. So please make sure you go see it. It's already being adopted by frameworks and some quantum chemistry simulations. Multi-GPU. So we have multi-GPU libraries, cuFFT, cuSolver, and CUBLAS. And the trend can continue in the future. I'm not going to go over the details because you probably want to see some performance results, and I have nicer charts than the ones below. So cuFFT. So I made a claim early on that we keep improving performance, and hopefully this convinces you Easy way to walk through the chart is like the left-hand bunch is a 256 cube, right-hand bunch is a 512 cube. This is complex to complex 3D single precision FFTs, and we're running on a DGX2. So you see 1, 2, 4, 8, and 16 GPU results. And we didn't scale very well. If you look at the gray line, which is Cuda release 9.2, the checkered is 10.2, and our next is in development, let's say, will be released at some point, hopefully in the near future, is you can see the kind of improvements that we've been making release to release. Especially it's quite dramatic for a larger FFT on a 16 GPUs. And if we focus on really large FFTs, and this is something that keeps coming up from applications that are running on the Summit supercomputer, or oil and gas applications, for example, I have a 1024 cube, a 2048 cube, and a 3072 cube FFT, again with the same legend, and using all 16 GPUs on a DGX2 computer. And this number is quite shocking to me, to do it in 0.44 seconds, and these flop rates are quite high. There's a paper from the Exascale project for a double precision FFT. They get, for a 1024 cube, so it'd be compared to this one, for a 1024 cubed, they show under 5 teraflops. And our double precision number is about half of this. So in a machine that's compared to using tens of thousands of GPUs to just 16 GPUs, we can get very, very, very high flop rates that are not possible to do anywhere else. The primary reason for it is FFTs are notoriously memory bound, and the DGX2 has, I think, 2.5 terabytes of aggregate interconnect bandwidth between the GPUs. So if you have applications like that, strongly encourage to seek a machine to at least benchmark and see what kind of performance you can get. And the last topic is cuSolver multi-GPU. I'll skip this one in the interest of time. I promised I'd go over time, so I'm fulfilling my promise. So what we're looking at here is the CUDA 10.2 performance, and we're looking at LU factorization and dense eigensolver. Both of them are dense LAPACK functionality. And we are extracting all the eigenmodes before anybody asks. And we're doing a scaling study up to 16 GPUs. But what we do is we fill the GPUs. So we run the largest problem that actually fits. So this is kind of like the maximum flop rate you can get at that number of GPUs. If anybody's interested in the previous slide, I have weak scaling numbers. And you can see on the right-hand side, I basically plotted it against the ideal speedup. And up to 8 GPUs, we get very, very good scaling in the sense that how well do we utilize the hardware if the machine is fully loaded? And that's very, very good. There's still some work to do, of course, for the 16Ks, because that's quite a bit far from where 16 is, and that's something that will improve in the future. And in closing, how can you help? So one of the most frequent things that happens is people coming and saying this doesn't work, that doesn't work, and that's fantastic. We want to hear about it. We want to hear all the bugs and issues that we have so we can go fix them. If we don't hear them, we can't fix them. And your feedback on the early access products or anything else, that's what helps shapes our products. If you have an application and you tell us, and I'm sure Sarah's nodding her head because she feels, and so is Pat, this is how software or ISVs, or we're not an ISV, but we're like an ISV within NVIDIA. We need feedback. That's how we decide what to do. We need to understand your applications, and we need to understand what's not working or how we could help you, because we just build the tools that let you do your work, right? And if you want to really help us, you can go to our career site and join us. All right? So I'll stop there. Thank you.